Okay, let's just dive right in. Imagine this for a second. You're in a reprocessing room, and in front of you is this incredibly complex, very expensive endoscope.
Mm-hmm.
It's just come from the procedure room, it's had its bedside pre-clean, and now, before you do anything else, there's one single step.
Just one.
And if you miss this one step or, you do it wrong, you've just wrecked thousands of dollars of equipment and maybe even put a patient at risk.
Absolutely.
So today, our mission is a deep dive into that exact step. The protocols for endoscope leak testing. We've gone through sources on aseptic technique, and this is really the foundation.
It really is.
I mean, the stakes are not theoretical at all. This is the moment
exactly.
we're checking the actual mechanical integrity of the system.
Exactly. And if you skip it or even just rush through it, water will get inside during the cleaning that follows. It's a guarantee.
And that water causes, well, what does that cause?
Well, it's a double whammy, really. First, you've got the financial hit. Water damage means an immediate expensive repair. We're talking tens of thousands of dollars potentially per scope.
Wow.
But the clinical risk, I mean, that's the one that really keeps people up at night. Once water gets into those tiny internal channels,
This is for breeding ground.
it becomes a reservoir for bacteria, for bioburden. And if that scope gets used again, the risk of patient infection just skyrockets. You're looking at serious health issues and, frankly, major legal problems for the hospital.
So this test is the firewall.
It's the firewall.
And our sources are really clear on this. Before you even start, you need full PPE.
Oh, absolutely not negotiable.
Personal protective equipment. So that's the hairnet, mask, goggles, or face shield, gown, gloves, the works.
Both for you and to protect the equipment from any cross-contamination. So let's dig into the three main methods. We've got dry mechanical, dry manual, and wet manual testing.
Okay, let's start with what seems to be the gold standard, the one you see most often in busy endoscopy centers, the dry mechanical leak test.
All right, this is the one that uses an automated machine.
So what's the prep for that? It's not just plug and play, is it?
Not at all. The prep is so important. First, you have to remove all the detachable parts.
So like suction valve, the air water valve?
Yep, the biopsy cap too. All of them. They get processed on their own. Then you connect the special leak testing valve from the scope to the machine.
Okay, seems straightforward enough.
Well, here's a detail that often trips people up. It's about how you position the scope.
Positioning.
Yeah. If you put the scope in a small basin for the test, you have to be really careful not to coil it too tightly.
Why? Why would overcoiling be a problem?
It's like kinking a garden hose.
Yeah.
A tight coil can create these pinch points, and that can actually hide a small leak. The machine won't be able to detect the pressure drop properly.
So it gives you a false pass.
Exactly.
Yeah.
A false sense of security.
Yeah.
The scope needs to be in a relatively relaxed position for an accurate test.
Got it. Okay, so it's hooked up, it's positioned correctly, and you hit start on the machine. Now you can just, grab a coffee?
Definitely not. This is where the technician's job is so critical. It's not passive.
Right.
While that machine is running and monitoring the pressure, you have to be actively working the scope.
What do you mean by working it?
You have to tune the knobs, flex the bending section all the way up, all the way down, right and left. You press all the buttons, image capture, freeze, you name it.
And you're doing that to sort of simulate what it goes through in a procedure.
Precisely. You're stressing the system. Those knobs and buttons are sealed with these tiny little O-rings.
Ah, the O-rings.
The O-rings are everything. They might hold pressure just fine when the scope is sitting still, but the second you turn that knob or press a button, you put stress on that seal. If it's worn, that's when the leak will show itself.
So if you skip that step, you've basically done a useless test.
You've done a useless test. You haven't checked the most common points of failure.
Okay, so the test runs, you've done all the movements, now you're waiting for the result. Pass or fail?
Right. If you get a pass, great, fantastic news. That scope is sound. It moves on to the next stage, which is manual cleaning.
Simple enough, but what if it says fail?
Okay, fail means you stop. Everything stops. You cannot proceed to cleaning.
Right.
The first thing you do is troubleshoot your own setup. Go back and check all the connections. Is the tube from the machine to the scope loose? Is the tube itself cracked? You fix anything that looks off, and then you run the test again.
Hoping it was just a simple user error.
Exactly. You always hope for that.
But the stakes go way up if it fails a second time.
They do.
Mm-hmm.
A second fail means the scope itself is breached. And now you're in a whole different protocol.
An emergency protocol, almost.
You could call it that. At this point, you switch the leak tester to constant air.
Okay, so it's just pushing air through continuously.
Right. And you are now looking very, very closely at the scope, especially the distal tip, the very end of it.
What are you looking for?
This is the single most important observation you will make. It determines whether or not that scope can ever be submerged in water again before it's repaired.
Wow. Okay.
So outcome number one, under that constant pressure, you see the bending section, that flexible tip, start to inflate. It distends like a little balloon.
And that's good.
It's the better bad news. It means the inner channels are probably still sealed, but the outer sheath has a hole. In that case, you can submerge the scope, clean it carefully, and then send it for repair.
Following the IFUs, of course.
Of course, the IFUs, the manufacturer's instructions for use, they are the gospel. You never, ever deviate.
Okay, so that's the better bad news. What's the really bad news?
The really bad news is outcome number two.
Hmm.
There is no visible inflation, no distension at the tip at all.
Mm-hmm.
But you know there's a leak somewhere because it failed the test twice.
Then what happens?
Then you absolutely must not submerge that scope. Do not let it touch a basin of water.
Why not?
Because no distension means the air is escaping fast, probably from a major breach directly into the core of the scope. If you submerge it, water will flood the internal optics, the electronics.
Catastrophic damage.
Total catastrophic damage. It's often non-repairable after that, or the bill is just astronomical.
So the fate of a, $100,000 piece of equipment rests on whether or not the tip puffs out a little bit.
That's it. In that second scenario, you only clean it externally. Meticulous wipe down. Then you pack it up and send it for repair, again, following the IFUs to the letter.
Incredible. So we've covered the dry mechanical test in detail, but there are other methods. What about the dry manual test?
Oh, right. So the dry manual test is often a backup or used in places that might not have the big automated machine. It's more portable.
And it relies more on the technician, I'm guessing?
Entirely. The prep is the same. Remove the parts, hook it up. But instead of a machine, you have a hand pump with a pressure gauge.
You pump it up yourself.
You pump it up to the required pressure, and then you do the exact same physical manipulations. You turn the knobs, press the buttons, all while watching that little needle on the gauge.
And if the needle drops?
If the pressure drops, it fails. Scope goes for repair. If it holds steady for the required time, and you can't rush this, it passes. It's effective, but yes, much more room for human error.
That makes sense. Okay, now for the one that sounds a little risky given everything we've said, the wet manual leak test. Submerging it in water.
It does sound risky, but it's a very old and effective way to find the exact location of a leak. You can see the bubbles.
So what's different about the prep here?
Again, remove all the detachable parts. But, and this is a key detail, if you're working with a specialized scope, like an ERCP or an EUS scope.
Right, the really complex ones for pancreas and bile duct procedures.
Exactly. Those have extra ports and electronics at the end, so you must put a special water-resistant cap on before it goes in the water.
Another one of those little steps that saves you from a massive repair bill.
A huge one. So the scope is pressurized, capped if needed, and then you submerge it, and you do the same thing.
Move the knobs, press the buttons.
And you watch. You're looking for a steady stream of bubbles. That's your leak.
Is there anything else unique to this test?
There is a very specific step. You have to infuse exactly 60 cc's of water through the suction port while it's underwater.
60 cc's, that's so precise. Why?
It's designed to put just enough stress on the seals around that suction channel. That channel is a major pathway for contamination, so you have to be absolutely sure it's secure. You push the water through and watch for any bubbles at the distal tip.
Okay, and let's say it passes, no bubbles. How do you get it out of the water safely?
Another critical moment. You have to keep the air pressure on while you take the scope out of the water.
Keep it pressurized.
Yes. You lift it out, dry it off, and only then do you release the pressure. If you release it while it's still underwater, the channels can create a vacuum and literally suck water back into the scope.
Wow. It's like every single step has a potential pitfall.
Every single one.
Well, that's a perfect transition. Let's talk about the big errors, the common mistakes that turn this whole process into a disaster.
And the thing to remember is, missing a tiny, slow leak is just as bad in the long run as missing a huge one. The consequences are the same.
Okay, so our sources point to 4 major errors. Number 1 is specific to that wet test.
Yes. Do not put detergent in the water.
Don't use soup. Why not?
It seems counterintuitive, right? And you'd think it would make it cleaner. But the soap creates its own bubbles, which makes it impossible to see the actual air bubbles coming from a leak. It just creates visual noise.
You blind yourself to the evidence.
Perfectly put.
Okay, error number 2, rushing.
A classic.
Yeah.
You have to give it time. A small leak might only produce a tiny bubble every few seconds. If you only watch for 10 seconds, you'll miss it. The pressure drop on a manual test might be very slow. You need to observe for the full recommended time, minutes, not seconds.
And error number 3 goes back to something you said was critical right at the beginning.
Failing to angulate, not moving the tip.
Not turning the knobs.
If you don't flex that bending section, you're not testing the O-rings under strain. It might pass a static test, but it's still a compromised scope, just waiting to flood during the next cleaning cycle.
Which brings us back to the ultimate impact of any of these errors.
Right. You miss a leak, water gets in. That water causes thousands in damage, and the scope becomes a potential vector for infection, completely defeating the entire purpose of sterilization. The leak test is the gatekeeper.
So when we put all this together, what's the big picture? It's this incredibly high-stakes process that blends mechanical engineering, infection control, and financial management.
It really is. The complexity is just immense, but it all comes down to that core mechanical integrity. The level of detail in these protocols, from stressing O-rings to deciding if a scope can be submerged,
Yeah.
it just shows that real hospital safety is built on an uncompromising attention to technical detail.
Procedural rigor isn't just a buzzword. It's literally the thing that separates a safe instrument from a serious infection risk.
Absolutely.
So this deep dive, for me, reveals that sanitation for these advanced instruments depends completely on their mechanical health. It's this world where tiny, invisible O-rings and carefully managed air pressure are literally the heroes protecting patients.
That's a great way to think about it.
So we'll leave you with this to think about. The lesson here seems to be that a mechanical failure is so often the root of an infectious risk. Now, if these sources focus so much on the vulnerability of seals and O-rings in an endoscope, what other overlooked mechanical failure points might be hiding in plain sight in other complex, life-saving equipment, from ventilators to surgical robots? What requires that same immediate, uncompromising attention before it becomes a risk? Think about the fundamental physical strength of the tools we trust with our lives.